Welcome to the second part of the ARSET training, crop mapping using synthetic aperture radar and optical remote sensing. On Tuesday, April 4th, we learned from Dr. Marino how to pre-process pulsar data, run Python code for machine learning of multi-temporal pulsar data to classify different crops, and evaluate the accuracy of the classifiers. Today's webinar, we'll be focusing on crop classification with a time series of optical and radar data from the Sentinel-1 and 2 platforms. Today's guest trainers are Dr. Krištof Oštir and Matej Račič from the University of Ljubljana, Slovenia. There will be one homework assignment for all 3 parts of the training. Answers must be submitted via Google Form, which can be accessed from the training page on the ARSET website. Homework will be made available on April 11th with a due date of April 25th. A certificate of completion will be awarded to those who attend all live webinars and complete the homework assignment by the deadline. You will receive a certificate approximately 2 months after the completion of the course from Marinus Martin. After participating in this training, attendees will be able to explain how polarimetric parameters are used for crop condition assessment, demonstrate how to perform Sentinel-1 SAR pre-processing to derive quasi-polarimetric parameters, perform a calibration of a SAR-based vegetation index to NDVI, monitor crop growth with multi-temporal polarimetric SAR data from Sentinel-1, examine crop growth using a canopy structure dynamic model and time series of Sentinel-1 imagery, and classify crop type using a time series of radar and optical imagery. It is now my pleasure to introduce the guest trainers, Dr. Krištof Oštir and Matej Račič. Dr. Krištof Oštir works at the University of Ljubljana, Faculty of Civil and Geodetic Engineering, as a professor of geoinformatics and remote sensing. He received his PhD from the University of Ljubljana and was a postdoctoral researcher at the Centre National de Recherche Scientifique in France. He has specialized in the use of optical and radar satellite imagery with a particular focus on radar interferometry, classification, time series analysis, and big data processing with artificial intelligence. He has led or collaborated on projects funded by the European Union, the European Space Agency, the Inter-American Development Bank, and National Geographic Society, and other national and international organizations. Applications of Earth observations range from agriculture and forestry to natural disasters, water detection, societal environmental impact, and archaeology. Matej Račič is an assistant and PhD candidate at the University of Ljubljana, Faculty of Civil and Geodetic Engineering. His research focuses on the intersection of remote sensing and machine learning. He started his academic journey at the Faculty of Computer and Information Sciences, where he gained extensive experience in data manipulation, algorithms, and machine learning. During his master's, he combined these fields to explore the field of satellite image time series, and since then, he has been utilizing his knowledge from both fields to tackle the range of challenges in Earth observation.
Thanks, Sean, for the introduction. My name is Krištof Oštir. I'm coming from the University of Ljubljana, and in the next couple of minutes, I will be presenting the crop classification with time series, optical, and radar data, together with my colleague Matej Račič. And I would also like to mention Anna Potočnik-Buchwald, who has helped us with the presentation and with the preparing of time series data. So to begin, we will start with satellite image time series. We will define what satellite image time series are. Then we will see where we can get this time series. We will focus a little bit on the Copernicus and the Sentinel series of satellites. We will define analysis ready data. We will do the time series analysis, and then we will focus on Sentinel Hub. We will use Sentinel Hub as the platform for processing the data, so we will introduce the Sentinel Hub statistical API, machine learning capabilities, especially EOLearn and EO workflow that is built on top of EOLearn. So let me start with the slide that you have probably seen many times. This is the Sustainable Development Goals, and in those 17 Sustainable Development Goals, space is present almost everywhere. I would like to invite you to have a look at the UNOSA web page, Space for SDGs, and see how space is being involved in the individual goals. Especially Earth observation is present in, for example, zero hunger, clear water and sanitation, life on land, life below water, so almost everywhere. But this was not the case in the beginning. We have to go many years back to see what has happened and how we have come to the situation that we are using Earth observation or remote sensing to monitor the Earth for a long period of time. But it was not until 1970s when Landsat was launched and Landsat changed on how we look at our planet. With the beginning of the imaging with Landsat, we are able to see what has changed in our environment on the whole world, actually, in the last 50 years. But what I believe is also a very important, or one of the most important things that has happened is the development of Sentinel Hub. Sentinel Hub was developed in 2000, was launched in 2016, and it actually changed how we process space Earth observation data by simplifying every aspect of this processing, by enabling processing huge amounts of space data without downloading the data, just doing it on the cloud with a simple scripts, and so that almost everyone can process terabytes or petabytes of data. Since then, many similar platforms have been developed. We have seen the expansion of Google Earth Engine capability, the launch of Microsoft Planetary Computing, and the others. Perhaps also to mention is the Copernicus Data Access Service that was launched this year to simplify the access to the Copernicus data. Okay, so we have long and dense time series. Satellite image time series, or SITS, as it is abbreviated, and you will see this a lot, are available for the last 50 years. Medium and high resolution data is available freely. What does it mean, medium and high resolution data? High resolution data is the data that is available at 10-meter resolution, so basically Landsat and Sentinel resolution data. We have Landsat archive that is completely open. In the year 2008, there was a decision to open the archive back to the first images that were captured by Landsat, and this enables us to see what has changed on our planet in the last 50 years. But when the Landsat archive was made open, this made an explosion in the exploitation of data. Since 2008, everyone is able to process time series of data. When the European Union was designing the Copernicus system, there was a lot of discussion of how to disseminate this data. Should the data be free? Should the data be payable? But at the end, it was a decision, and I believe it was a very important decision to make Copernicus data complete, free, and open. So when we begin with Landsat, we have data back to the 1972. However, those data is not very dense. We have Landsat data every 16 days, and in the last decade or almost a decade, we have data that is much denser. We have weekly data, we have daily data, and this enables us to process the information on the ground on a completely different way. And we also have harmonized satellite image time series. harmonized Landsat and Sentinel data, harmonized optical and radar data, harmonized Sentinel and planet data. And we also seeing harmonized optical and radar satellite image time series. So I already mentioned several times, everything happened with the Landsat. With the Landsat in 1972, and we have image of every area on the land every 16 days. However, Landsat is an optical satellite, and optical satellites are very much affected by clouds, and this can cause difficulties when we are doing time series analysis. Therefore, there have been many initiatives to densify those time series, to make those time series, let's say, weekly time series or even daily time series. And the European Union has launched the Copernicus program. So Copernicus is the program that is being financed by the European Union or its member states, and is currently the most sophisticated Earth observation system or system of systems. It is composed of a space component with a series of Sentinel satellites, from Sentinel-1 to Sentinel-6, and it is composed of Copernicus services. In addition to that, we have in situ component. The Copernicus services, which are maybe not as much known as the Copernicus satellites, are land monitoring, emergency management, atmospheric monitoring, marine environment monitoring, climate change, and security. There are many different organizations who are providing these services to the end users. And by providing these services means that these services are simple so that everyone, civil protection, rescue organizations, farmers can use these services. This is, of course, driven by users. Users are defining what Copernicus should do and what Copernicus should not do, and they are defining the program at a higher level. For the space component, we have the European Space Agency and EUMETSAT, European Meteorological Satellite Organization, who are defining and building the satellites. Actually, ESA is being responsible for the satellite launches and building, and also the operation of the satellites. And in the space component, we have a series of satellites coming from Sentinel-1, Sentinel-2, 3, 4, 5, precursor, and 5, and the Sentinel-6. In addition to that, Copernicus is providing data dissemination infrastructure. Because if we have such good quality data, if we have data coming from different platforms, we have to put this data into the hands of people. And by providing simple to use data dissemination infrastructure, we are able to give everyone access to this valuable data. So in the Copernicus space component, we have a series of satellites. Each satellite group has at least a pair of satellites, like Sentinel-1 A and B, which is for radar observations, Sentinel-2 A and B for high resolution optical observation, Sentinel-3 A and B for medium resolution imaging and altimetry, Sentinel-3, 4 A and B for the observation of the atmosphere from geostationary orbit, Sentinel-5 and with the precursor satellite for the observation of the atmosphere from low orbit. And what is really important here is this is just the first generation of the satellites. So every satellite will be replaced before the end of their life cycle by a new satellite. In our webinar, we will focus on the Sentinel-1 A and B and Sentinel-2 A and B, because we will be doing mostly radar and high-resolution optical observations. So let me begin with Sentinel-1. It is a radar satellite. The first one was launched in 2000 2014, the second one in 2016, and it is aimed at observation of land, forests, water, soil, and agriculture. It is also very important for rapid mapping in case of natural disasters. Sentinel-1 is also capable of doing ship traffic observation, observation of ice and sea. It is a C-band synthetic aperture radar. We will see what does it mean for the observation of vegetation in a couple of minutes. And it is observing the Earth in a 250 kilometer swath with a resolution of 5 by 20 meters, which can be resampled to about 12.5 meters. It is observing the Earth every 12 days. This is true for each of the satellites. And in the case when we had 2 satellites, this revisit time was 6 days. Sentinel-1 is also very important because of interferometric radar, because this enables us to observe the surface motion and also the vegetation if we are taking into account the coherence. This is a typical radar image where it's not very exciting. It's black and white. This is just one polarization. And what you can see on this radar image is, of course, the relief, which is very clearly seen on the images. You can see water bodies here. You can see water bodies over there. These are actually flooded area. You can see an urban area here, a river over there, and different agricultural fields in that area. The area here is covered with forests, and this is not clearly seen on radar image like this. Sentinel-2, on the other hand, is an optical satellite, and the first one was launched in 2015, the second one in 2017, and it is actually the satellite that was specifically designed for observation of vegetation. So it is a satellite designed for observation of land, water surfaces, coastal areas also, and soil, but the main focus was vegetation and agriculture. The orbit of Sentinel-2 repeats every 10 days with a pair of 2 satellites. There's the constellation of 2 satellites. It repeats every 5 days. The main scanner is the multispectral imager, which has a swath of almost 300 kilometers with different resolutions from 10, 20 to 60 meters. So if we observe the bands of Sentinel-1A and B, we see that they are almost identical satellites, almost but not completely. They are comparable, very well comparable, so they have bands that are very similar, but they are not exactly the same. So these are the spectral curves or spectral signature for different kinds of materials like soil, vegetation, and water. And here you can see the bands of Sentinel-2. We have one band, or a couple of bands. We have 4 bands with 10-meter resolution, which are in the visible part of the spectra and near-infrared part of the spectra. Visible part so that we have visible RGB images, and near-infrared part because of the vegetation. This is a typical Sentinel-2 image with the in the visible part of the spectra, the same area that was covered before. It looks much nicer. So you can see here forested area. You can see again the urban area. Water can be seen, but not that good as it was on the optical images, and you can see a lot of agriculture areas here. So you can see different stages of agriculture at different times. However, Sentinel-2 is an optical satellite, meaning that it is affected by clouds. This is the statistics of cloud coverage for the area of Slovenia, where we have some areas that have some images that have less than 10% of cloud cover, some images that have between 10 and 30%, and some images that have more than 30% of cloud cover. We are not able to get all the time steps that are available. We have we are theoretically able to acquire an image for the Sentinel-2 every 5 days, and even more frequent if we are at the latitude that are farther to the north or to the south. But in practice, cloud coverage is prohibiting this observation. So let's go back to time series and see how we generate time series, how time series are constructed. Well, what actually is time series? This is a set of images taken over the same area of interest at different times. The images can be taken by the same or multiple sensors. We can just have Sentinel-2, we can just have Landsat, we can just have Planet, and the images are taken with the same sensor, or we can combine this data together. And we are getting a stack that we are able to process at a time series. And time series enable us to understand how Earth is changing. They enable us to determine what causes the changes and predict the future changes, or what will happen according to what has happened in the past. In addition to that, time series enable us to discriminate features. There are certain features on the ground that we can only discriminate by time series analysis. For example, compare some wheat and grassland. At certain period of time, we are not able to discriminate between wheat and grassland because they look the same. They have the same amount of reflection in near infrared, the same amount of reflection in green and red. But if we take an image a couple of weeks later, a month later, we are able to discriminate these two land cover classes, so grassland and wheat or corn and so on, because of the typical time development of vegetation. So let's have a look at the time series of Sentinel data. Here at the top you have the date, and here it's the same date. On the left you have the classical near infrared red green visualization, and on the right you have NDVI. I was trying to construct a time series over the whole year, and I was selecting only cloudless images. So you can see very good images, and still there pop some images with clouds like this one here or this one here. And what is even more important, if you observe this date here, you can see that in certain months you don't have good quality data. So we are missing data in certain months. The time stamps are not following, let's say, 5 days interval, but there can be some gaps in between. If we do the same with Sentinel-1 data, you can see here the date, and you will see that the date is incrementing by 7 days. So I have selected one image every 7 days, and I could even select more than one image every 7 days. So for the radar data, we really have dense time series. Here you have the vertical horizontal polarization and vertical polarization. So you see the differences between these two. And it is really important that the radar is not influenced by clouds, and we are getting dense time series because every image can be included in this time series. So to be able to process time series, we have to have something that is called analysis-ready data. Committee on Earth Observation Satellites defines analysis-ready data as satellite data that have been processed to a minimum set of requirements and organized into a form that allows immediate analysis with a minimum of additional user effort and interoperability both through time and with other data sets. Blah, 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 it's called data which is ready to use. The end users like myself and you, we don't want to bother with all the processes that are behind. We want to have data that is ready for the analysis. We want to have data that has been pre-processed in a form that we can use Python scripts or any other scripts to analyze the time series of data efficiently without doing a lot of pre-processing. So what does it actually mean, analysis-ready data, and who's providing analysis-ready data? Well, in the past, the users had to do this by themselves, but nowadays data providers are generating RD data. And of course, RD, what is RD depends on applications. The first thing and the most important thing is, of course, image clipping. We have to get a data cube of the same area. This is very important because we are observing time series for a certain area. But we have to do also masking. Usable and unusable data masks are probably the most important factor in generating analysis-ready data. Because for the successful analysis, we have to know where do we have unusable data, where in our time series we should make a jump and not count data that is misleading. Because if we have clouds on the image, this is of course not the data that we would like to analyze with time series analysis. We just want to put not a value at that moment in time. Sometimes atmospheric correction is done, so the effect of the atmosphere is eliminated. We have to do the pixel alignment because we don't want to detect changes in time series data because the pixels are misaligned. And the pixels are misaligned depending on the system for a couple of meters or pixels. And this is a factor that we have to correct before doing the processing. And we have to do the sensor alignment or sensor harmonization. I already mentioned several times the Sentinel and Landsat and also the PlanetScope. And the end user, for example, myself, I don't need to know where the data comes from. I just want to know what is the reflectance, what is the NDVI at a certain period of time or a certain timestamp, and therefore we have to join this data together into harmonized time series data. An example of this harmonization is the Landsat Sentinel harmonized time series, where we are taking Landsat data and Sentinel-2 data, where we are doing atmospheric correction, geometric resampling, normalization, band adjustment, and then we are generating harmonized time series products in the grid of Sentinel-2, for example, with the resolution of Landsat, with the spatial resolution of Landsat, but at a much better temporal resolution. And such combined time series is really a valuable tool for the analysis. So what we have to do with the harmonization, when we have two different sensors, like the case here for Sentinel-2 and Landsat 8, you see that the timestamps are different, of course, because Landsat 8 is taking images every 16 days and Sentinel-2 is taking the images every 5 days. And this dense time series of data enables us to do a much better interpretation. Okay, what do we see on radar and optical images regarding the vegetation? This is also a very important factor. We have seen these spectral signatures in the past, and you probably were aware of those curves. And here you can see the typical response of vegetation to different wavelengths. We are seeing a strong reflection in green, a very strong reflection in near infrared caused by chlorophyll in the leaves, and we do see some absorption bands here caused by different compounds or chemicals like water present in the vegetation or water presence in the soil like here. And this is what we are trying to observe with multispectral data. With multispectral data, we are generating or collecting bands at different wavelengths. But indices are those who take the advantage of this wavelength characteristics. So, for example, we are using vegetation index or any other index to observe the vegetation. Regarding the radar, the situation is even more complex. For the radar, we have different frequencies, we have different bands, as they are called. The frequency or wavelength can be 3 centimeters, 6 centimeters, 24 centimeters, or 65 centimeters. And depending on this, the radiation is being scattered either on top of the vegetation, like in the X band, or at the bottom or in the middle of the vegetation, like for L band and P band, or somewhere in between, like the situation is for the C band. So for the radar backscattering is influenced by the characteristics of the radar and of the surface. We have the wavelength and frequency, we have the polarization, either horizontal, vertical, or combination of those two. The radar has a typical incidence angle and of course a typical resolution. These are all the characteristics of the radar system, and the user cannot influence them. And then we have the surface. We have the surface with different structure, with different phenomena on the surface, with different roughness of the surface, with different conductivity and the electricity of the surface, and with different orientation. For radar backscattering, the orientation of the fields of the structures on the ground can change the backscattering drastically, or this is what we can observe on radar images. One of the features that is extremely valuable with radar is also radar interferometry. In addition to backscatter, radar is also measuring the distance between the satellite system and the ground. So radar actually measures the distance from the satellite to the ground, and this can then be used for different purposes, especially if we are observing images taken from two slightly displaced orbits. If these two orbits are displaced by a couple of meters up to a couple of 100 meters, we can process the data in interferometric way. In that case, we have phase differences between these two images that are caused by different factors. The first one is parallax, because the images are not taken from the same position. The second one is elevation differences. We can observe surface movements. We can observe, or we are observing, atmospheric phenomena. If we eliminate this atmospheric phenomena, and we know the parallax because we know the position of the two satellites, or where the images have been taken, we can observe, for example, the elevation on the ground if the surface movements are not present, or surface movements if we do know the elevations. So radar interferometry can give us elevations in the meter accuracy and displacements in the millimeter accuracy. But for observing the vegetation, a side product of this interferometric processing is extremely popular or important, and that is the coherence. Coherence is a measure of how well two image pairs correspond to each other. The coherence of an insert data pair represents the magnitude of the complex correlation between two images on a pixel by pixel basis, meaning that for each pixel we have a correlation between the images taken a couple of days apart. This is the case of Sentinel-1, where the images are taken 6 days apart, 12 days apart, and 18 days apart. And you can clearly see how the coherence is getting lower and lower. And coherence is a measure of amount of noise in the interferogram, and coherence is a measure of the development of vegetation. Because in 12 days or 18 days, the vegetation is being developed or is changing, and therefore the coherence gets lower and lower. It still remains very high in urban areas because there's not a lot of change over there, but wherever we have vegetated areas, we are getting lower coherence. with a longer time span. So if we have a change of coherence between two images, it means that something has happened to the vegetation. Either vegetation has grown, or the crops have been harvested, and so on. So the coherence of the interferogram is a direct proxy of the development of vegetation. Yes, but with optical data, people are mostly using NDVI. And is NDVI enough, or do we have to use other indexes? So there exist many vegetation indexes. The basic one is the classical vegetation index, which is a ratio between near infrared and red. Since this index is not normalized, NDVI, or normalized difference vegetation index, is being used very often. So the difference between near infrared and red divided by the sum near infrared plus infrared is the most commonly used vegetation index. It is normalized to -1 and 1, and it is very easy to interpret. In addition to that, many other indices exist, like enhanced vegetation index, the soil adjusted NDVI, and others. If you have a look at the index database, you will see many of those indexes listed, including with the equations, and I suggest that you have a look at this index database and to see what indexes are available and if they are suitable for your purposes. So this is just a shorter list from index database with the tag agriculture, where you can see the first 16 indexes with different equations suitable for different sensors, suitable for different application. And of course, by so many indices, the very important question is which one is the best, or maybe if I say which one is good enough. So if we are looking at the Sentinel-2 bands here, you can see this is a smoothed curve of the development for 1 year. You can see that these reflectances increase during the summer and decrease in the winter, and they are lower in the beginning of the season, but they almost all follow the same curve. And here you have the same situation for different indices. The first one is NDVI, and you have the NDVI here. Very easy to interpret curve. In the beginning of the season, it increases, and then it decreases at the end of the season. And more or less all the other indices follow the same curve, follow the same pattern. They are just shifted a little bit, and probably they are very much correlated. And this is true. If we see the correlation between 22 images, 22 indices here, NDVI is the first one, so the correlation between NDVI and the 21 remaining indexes that are listed here, you can see that they are not just slightly correlated, they are extremely correlated, or they are almost the same. So to answer the question from the beginning, yes, NDVI is probably enough. Okay, we have defined the time series, we have defined how we generate time series. Now we have to go to the time series analysis for vegetation mapping. Here you have a tree and the yearly development of this tree. In the spring we have very bright green leaves, then we have in summer they are starting to brown a little bit, and then you have autumn and winter where there are no leaves on the tree. If we are taking the observation of NDVI, we have seen a yearly cycle. So in the beginning of the year, the NDVI is low, then it starts to increase. It gets the highest point, and then it decreases in autumn. This is for the northern hemisphere, of course. From this curve, we can define the vegetation parameters. We can define the beginning of the season, we can define the end of the season, of course, the length of the season, the base value here, the middle of the season with the highest value, the maximum value here, and of course the amplitude of this development. And this enables us to observe different vegetation types. This enables us to observe different crop types and to define the parameters for the crop growth. Just to remember, we have very green leaves or green leaves, then we have red leaves, we have yellow leaves and brown leaves, and this is all related to spectral signatures of these leaves. So then the NDVI changes. This is for the green leaf, and for the other leaves, the spectral signatures are a little bit different, and vegetation index, which is a ratio between near infrared and red, reflects this development very well. Okay, let's have a look at what we see with the development of vegetation. This is the NDVI development for European beech, Fagus sylvatica, and here below you can see the images of the same tree during the whole year. Why is this important? Because I want you to have in mind that what we see with satellite image time series is not exactly what the observer on the ground would notice. For example, for the Fagus sylvatica, we have observers who are observing the beginning of the season for different tree types or different crop types. And when they mark the beginning of the season, they mark it at the time where they see the first green leaves on the plant. And this is, of course, not something that we cannot see on satellite images. The trees, the vegetation has to develop much further so that we are able to see the increase over here. The same is at the end of the season. The observers, the in situ observers who are marking their calendars and generating the databases of different tree or crop types, they're seeing the browning of the vegetation, something like that here. And again, this is not something that we are able to detect with satellite image time series. We might detect this before or after actual browning is being marked on the calendar by in situ observers. So we have to have in mind that while we are observing the length of the season, this might be a factor that is not the same as a human interpreter is doing on the ground. There's nothing wrong with that. We have to just know that the start of the season and after end of the season have to be shifted a little bit by maybe a couple of weeks according to the observations that have been done by in situ observers. Okay, let's move to time series of images. Here you can see the development of agricultural fields from April to November. And if I show you this, you would immediately be able to recognize the development. You would say probably immediately that nothing is happening in April and May, but then still things start to develop in June and July when certain fields are completely differently colored, so different crops are growing. And then in August and September we have harvesting, and we are seeing a lot of bare soil. So when we are doing time series classification, we can do it in several ways. The first one is to do it in a quasi time series classification. What does it mean? We just stack the time series of images one above the other. For example, we take the time series of NDVI and stack this time series one on top of the other, and we are getting kind of multidimensional data, and we are doing multidimensional classification. This is exactly the same as we are doing multispectral classification on one image, except that we have one multispectral image with, let's say, 13 bands. In our case, we might have one multidimensional image, one stack of images with, let's say, 20 or 30 bands or timestamps, and we are doing the classification. In that case, we are classifying with this stack of images, but the time sequence is not really considered. The classification is being performed on a time signature of event, like the multispectral classification is being performed on spectral signature of the event. However, more important is do the full time series classification, where we take into account the development of the time development of different features. And here we have to deal with different distances. We are comparing time series, and we cannot just compare time series in Euclidean way, because we might have some changes between different years, between different features in different areas. So we have to do something more sophisticated, like this dynamic time working, where we adapt the beginning of the growing season or any other element, and we stretch a little bit this time series so that we are able to compare similar events with different time series. Time series classification takes many of the algorithms or methods that have been developed for speech recognition, because for speech recognition, the first obvious thing is time shift, and then we have different frequencies, different speeds of talking, and for doing correct speech recognition, we have to do a lot of dynamic time warping. So how do we do classification based on time series? We have a series of known time development, like the case here for barley, maize, rapeseed, triticale, and wheat. And then we have a new unknown time series, and we want to compare this time series. As I have shown previously, we compare the differences between the unknown and the known time series, and we classify the time series into the class that is closest to the unknown series. You have probably done many times the single image multispectral classification, and there we are dealing with spectral signature, and this here are actually time signature. So every crop type, like triticale here, has a characteristic time series signature, in the same way that every crop type has a characteristic spectral signature. Yeah, until now I have shown you mostly beautiful time series, but life is not that beautiful, and when we are dealing with, especially with optical data, but also with radar data, we are getting a lot of noise. This is an actual time series collected or generated straight from data coming from images. You see a lot of noise, a lot of jumping up and down. And is this jumping up and down influenced by clouds, or is it real development? Is it harvesting of crops? Well, we have to do the time interpolation or time integration. This is the image with the time series without aggregation. This is the time series with 5-day aggregation, where you can see that some noise have been eliminated. This is the time series with 10-day interpolation and with 1 month of interpolation. So in this case here, we have 1 point in time every month. And this is probably enough for time series analysis, because you can clearly see the development of different tree types in that case, and we don't have a lot of noise. Another factor that is very important is time synchronization. Satellite images have different timestamps. They are generated regularly every 5 days, but then we have overlapping orbits or overlapping scenes when we get information either every 2 or 3 days at northern and southern latitudes, and we have images coming from different satellites and different sensors. So to be short, our time frequencies are not equally spaced. We don't have equal timestamps of the observations, but they can be like this is the case again for Sentinel-2. They can be around 5 days or less, but we can have also images that are taken 15, 20, 25 days or 30 days apart. So we have to synchronize the timestamps. This is the original Sentinel-2 NDVI time series. What you can see here is, of course, a little bit of noise jumping up and down. And what you can see also is that in some time spans, we have a lot of data. We have images really every 5 or 3 days. But there are time spans where we don't have any information, or we are having missing data because of the clouds and so on. So what we have to do is we have to compare time series like this, which is not uniformly spaced. And this is spaced. And this is difficult to interpret. That's why we are introducing weekly averages, where we take the timestamp every Monday or every Sunday in the week and compute the values over there. Or we can even do monthly aggregations. What we can do with NDVI, for example, is to use the maximum NDVI or the mean NDVI in the period of 1 month. And in that case, you see we have a similar development, but much easier to interpret time series as this. In addition to that, an important factor is how long must the time series be? When can we classify the features on the ground? Do we have to wait until the end of the year, or can we do the classification after 1 month or 2 months or a couple of months? And we also have to consider, are we comparing the data for this year with the data coming from previous year? So we have to see, is it enough to have the data just for the first 2 or 3 months, or do we have to have more information? Probably at this stage here, we will not be able to classify different crop types. But if we are going further in the year, like to June, we would be able to increase the accuracy of classification significantly. So here at the beginning, the classification would be of very bad quality, but when we are taking more data into account, we can have better quality data. Meaning that the beginning of the year is enough for the classification of different crop types. Why is this important? Because if we would have to have the whole yearly time series development, this would mean that we would be able to do the classification at the end of the year, basically for the previous year. But what we would like to do is to be able to do the classification in the beginning of the year and to be able to classify after a couple of months. We also have to compare this data with previous years. Here you can see the development of the same crop in different years, and you can see that the years are comparable. However, the starting of the season is being shifted according to the shifting of temperature and precipitation for that year. So it's basically the influence of climate and climate change, if you would like. But you also see some anomalies on this time series, and these anomalies are those that we are interested, because that can mean either some natural disaster, it can mean drought or the impact of drought, or a similar event in the crops. Okay, so we have now seen how to generate time series, and now we are moving a little bit to the practical part, and we will be discussing the Sentinel Hub. Copernicus data, that's petabytes of data generated every year, has to be put in the hands of users. European Commission is very well aware of that, and that's why they are developing simple tools to use this data. And this year they have launched the Copernicus Data Space Ecosystem, the CDSE, to be the new way to get Copernicus data. In the past, this was kind of neglected by the European Commission. The Copernicus Data Hub was providing the data, but the interface was not very efficient, and it was hard to get right data very quickly. And that's why the Commission, together with the European Space Agency, is launching the Copernicus Data Space Ecosystem that will allow the search and API access to different data, and of course the processing in Jupyter notebooks in the cloud with different technologies. And here Sentinel Hub will be one of the most important or the central parts of this initiative. The Copernicus Data Space Ecosystem will be fully operational this year. Now it is, you can also already try it, and there'll be new functionality coming to the end of the year. So what is actually Sentinel Hub and what does it provide? Sentinel Hub was launched in 2016 to simplify access first to open Earth observation data, to the Sentinels, to Landsat data, to MODIS data. Later, also commercial Earth observation data was made available through Sentinel Hub, and the users can also add their own data like raster and vector data, digital elevation models, other vector data like land parcels and so on, but also drone and airborne data. Sentinel Hub is following the OGC standards and provides VMTS, VMS, and VCS services that the end users can use in their cloud GIS, web and mobile applications, desktop GIS like QGIS or ArcGIS Pro, and most importantly, they're able to access Sentinel Hub through scripts, to Python API, to R scripts, to NV scripts. And this is actually a game changer in the frame of Earth observation. You don't have to use any sophisticated data provider to generate time series of data. You can use one service, Sentinel Hub Statistical API, to get time series and to analyze time series within the same script. So if you register and join the community, you are able to launch the Sentinel Hub Playground or AO browser, and you're able in seconds, really in seconds, without knowing any programming, generate products with this. You can make this nice visualizations by using different band combinations like here, and with a little bit of knowledge, you can process petabytes of data in seconds on a really old computer. You just need a browser and a little bit of JavaScript. And if you give this power to people, magic happens. Applications pop up where you expect them and where you don't expect them. In agriculture, in forestry, in water management, in monitoring air traffic or trucks from space, in monitoring ships from space, in every domain that you can imagine, and there's someone who has a little bit of knowledge, a little bit of courage, that writes a script and processes the data and generates the results. This is really a democratization of Earth observation. Now, it is not everyone can use their own computer to see what is happening to any part of the planet. So how to use this data and how to get the benefits of this? First, you have to create the Sentinel Hub account. Just head over to sentinelhub.com, Google it, and then click on the sign in button. Okay, so now I suggest to move to the browser and to do the live demonstration. So head over to sentinelhub.com and you have here the sign in button. If you click the sign in button, you will be going to the sign in page, and here if you don't have the account, you have to sign up for account. So just click the sign up button and enter some user details, first name, last name, and very important, enter the email address here. You have to generate a password, confirm the password, and agree with the terms of services. And then you click the sign up button. So when you create a Sentinel Hub account, you will enter the trial mode, and you have to send your registered email to my colleague Matej, matej.račič@uni-lj.si, because you will get credits for processing and advanced use of Sentinel Hub. European Space Agency and Synergize are sponsoring the use for all the ARSET participants, and you will have enough credits to do time series analysis, including the machine learning with that credits. When you have registered for the Sentinel Hub account, just log in on the page. So enter your username and password and click sign in, and you will be immediately transferred to the dashboard, where you can see how many credits you still have, what is your usage, and so on. And then switch over to the EO browser, or you can just search for EO browser. And Sentinel Hub EO browser is the way to go. And when you enter the EO browser, you can continue with the tutorial, or you can just skip the tutorial and log in. Once you log in, you will see here, it means that I'm logged in. You can change the language to any other language, and you can start exploring the data. I will move to a part of Slovenia here and try to search some images. You have Sentinels, Sentinel-1, 2, 3, and 5P. You have Landsat data. You have even the harmonized Landsat Sentinel data. You have other data like MODIS, digital elevation model, and even Copernicus services. We will focus on Sentinel-2 data, and I will click here on the advanced search. And first, I will lower the cloud coverage to let's say about 20% approximately. And I will be searching for Sentinel-2 data and the Sentinel-2 level 2A. Of course, I have to change the dates, and I will try to search for some images in the summer of 22. So let's say from the 1st of July to the end of August. So let's click here. We have here the date range from the 1st of July to the 31st of August, and we will do the search. Immediately you get the search results, and you can visualize one of the images. So this is the area. You can move out, you can zoom in, zoom out, you can move around and change the visualization. Here we have the true color image. You can switch to false color image, and this is processing on the fly. You can do some other combinations like NDVI. What Sentinel Hub is doing, there's nothing pre-computed. Immediately when you click another visualization, it is getting the data, processing the data for the frame that you are looking for, the area that you are looking. This is extremely fast, but it takes some computational power. So I will switch to NDVI. Now we have the NDVI for the image, but you can also select any of the other layers here, or you can create a custom script. So you can create a custom visualization with different band combinations, and it is computed immediately without any, or almost without any delay. I will go back to this prepared visualization, and I will click NDVI, because we have seen that NDVI is very good for vegetation observation. Okay, so now we have here NDVI, and you can see different fields here. Again, if we switch to true image, you see that there are some agricultural area here, and you see some narrow fields. Switching back to NDVI, I will try now to generate the statistics for the area that is shown here. What I have to do, I can put a marker in the area, and when I put a marker on the area, I'm getting here a new toolbar, including the statistical info for this area. And if I click this statistical info, the time series of NDVI is being generated. So I'm getting 1 month of data for this point, for the point that was selected, and you can see here the time development for 1 month. Of course, I can change the cloud coverage, and I'm getting less data points. But what I would like to mention is here the export CSV button. This button exports my time series to a file that can be analyzed later. Okay, so let's use another tool. I will use this area button here, and I will draw an area. I will manually draw an area. I will try to select a field. So I'm clicking, and I will finish with the second click. So clicking on the first point. So I have here an agricultural field, and I can generate the statistics for this field. This is 0.04 square kilometers. I can generate the statistics in the same way. So now I'm generating Sentinel-2 level 2A statistics, and you can see not just statistics for 1 point, you can see also the standard deviation for those points. And again, we can make 2 month statistics, and here you can see that this is computed on the fly, and we have to wait a little bit that the statistics is calculated, and we have to lower the amount of clouds that we allow in this statistics. So we are eliminated cloudy images, and we can go to 1 year. And in that case, it will take another couple of seconds to compute this statistics. And after we have done this, we can export the statistics to a CSV file and analyze this CSV file later. Okay, the statistics has been computed for 1 year, and I just for the demonstration purposes, I will click also the 5 years, and you can see how now the computation of the statistics is going back 5 years in time. So this means that every image for the last 5 years is being loaded. The statistics is being computed on this polygon, and the statistics is being displayed here and stored, and we can see the time stamps where the images have been taken, and I can even lower the amount of clouds that I allow, and this changes a little bit the time series. This will take some time because there have been a lot of images taken in the past five years, so we have to be patient. And of course, this is in this case we are using a certain amount of credits for this computation. Okay, so we are almost finished. Okay, a couple of seconds more, and we will have the complete 5 year time series for this field. And by clicking the export button, my file is being downloaded and stored locally. and I can then open this file and use it with Excel. So with EO browser, we can generate time series of any of the layer that is present in the EO browser. We have seen Landsat, MODIS, harmonized Sentinel-2, Landsat time series, and of course also the Sentinel-1 data. Here we can see the vertical, horizontal polarization, the gamma. Here you can see the time series of radar data for the point shown here, or we can see the time series for optical data, Sentinel-2 level 2A time series, where we can reduce the amount of clouds and get a less noisy time series, and where we can increase the time series to get a 5-year time series, like it is the case here, where you can see the development of vegetation in this point or polygon, and you are able to do the time series analysis later. If you export the data to Excel, you have a table like this. You even have the cloud coverage percentage, and you can filter and select only the pixels that do not contain clouds. And in this case, this is cloud percentage per selected area. So for my polygon, this means that these images did not contain any clouds. And we are getting the minimum, maximum value, the mean value, and the standard deviation. And this can be then used in time series analysis in Excel if you want, which is a simple way to use this kind of data. So we are now moving to the integration of radar and optical data and the machine learning part, and I will be heading the word here to my colleague Matej.
Thank you for the introduction and welcome. We'll take a look at radar and optical integration, and without further ado, let's get started. There are a few ways we can join this information. We can combine both radar and optical. By doing so, we wish to combine both of best worlds. This can be done using machine learning, data fusion, and with this, we are hoping to create a combined radar optical vegetation index, which can serve us for various applications in natural environment mapping or monitoring. One of such applications could be crop classification. As we can see in radar backscatter, there are obvious patterns and differences between wheat and barley, and even between different years. Similarly, it can be observed in optical indices. Comparing here, we can see both NDVI and NDRE. We can see there are quite a few differences in various crops, such as winter wheat, cotton, spring maize, and other various vegetation types. One of such applications can also be mapping grasslands, intensive and extensive. This can be done by tracking when a certain parcel has been mowed. This can be visible in both radar and optical information. For example, in NDVI information, we can see the value dropping once there was a mowing event, and then quickly rising after as vegetation recovers. And we can see this pattern multiple times a year. Similarly, in case of coherence, we can see the values increasing as the change has happened in the parcel. And now, if we start with the machine learning, quite often to referred as AI, artificial intelligence. If you're following any new publications and the news, must have heard of GPT-3, of OpenAI's new endeavor. But this is quite often actually just machine learning, more specifically deep learning, which is a subcategory of machine learning. And the main difference between the two being the method that we use. Specifically, deep learning is more complex, or actually the methods that we use have more layers, but more about that in the next slide. All machine learning has in common is the way that we need to formalize our problem that we are solving, addressing. Whatever we are doing, we have to first define what is the result that we're trying to achieve. So if we take a look at remote sensing, for example, a little bit more of intuitive problem that we're trying to solve would be scene classification. And this would mean, as shown in this example, that we're actually trying to give a label to the image and define what it is that it is representing. In this case, I'm pretty sure that we can say that this is the residential area, and we can all agree. But we can also see that there are a few roads and a few trees in the image. This makes it a little bit harder for the model to differentiate, but we can still see that it has no issue with the given image. Making the task a little bit more complex would be object detection. This would mean that we still have the same input in the entire image, and we output each bounding box for each object that is detected. And we can see that in this case that we have buildings properly detected and also a car that is marked. And we can see that each object has a probability. So this means that each individual object has this similar labels as we had before, and then the probability that it belongs to that specific class. While going even further, we have image segmentation. We still have the same similar input, meaning that we input the entire image, and now we provide the segmentation over the entire image, meaning we classify each pixel, we give the output, and we can see this also as an image. And if we take a look now for the green pixel, we can see that it belongs to building, but it could be also road, plants, and water. But as the probability is highest for the building class, this is also what is indicated in our output. But what is different for the examples that we'll be looking at is actually a pixel classification, which differs from segmentation specifically on the area that it does not include the information from neighboring pixels, but only for that specific one. We could produce similar results as we have them here, but in image segmentation, but this is not the case, but this is not, the input is not always the entire image, but just each individual pixel. This means that we can use different methods and different optimizations to achieve similar results. And if we go a little bit more specific into machine learning for pixel classification, let's say that we are using decision trees. As we have an example here on the right, our decision tree expects two pictures as an input, normalize different water index and normalize different vegetation index. And based on whether the value of water index is above 0, we give it the value is true, and we mark it as a water body. And if it's lower, we check the value of NDVI, and based on the predefined threshold that is actually inferred from the training data, we divide it into the other two classes. But this here is only an example, and the trees can and are more complex and are inferred during the training. This is actually when we prepare the data, we have to predefine what our samples are, and each sample has to have a label. And based on that, based on the distribution in the data that we have, the model then learns which pixels belong to a specific class, and then is able to come up with these rules. And with this, we are able to have a simple classifier that is able to produce a cover map. But even going further from this and making it a little bit more complex is the random forest, which combines decision trees, a lot of them, and those trees actually always work on a subset of the data that we have, of the samples, both in the number of samples that it works with and with the features that we're working with. This is often quite important, as the trees would not differ if they all had the same data. This is why all trees are actually working just on a subsection. Maybe they don't have all the features, or In this case, maybe they're all working only on vegetation, maybe only on the water indices. But this is also then expanded when we have multiple steps of the time series and more features. Then they can adapt to specific classes or to specific conditions, and they are able to perform better than a single decision tree, as they are an ensemble, and they're able to vote to what they think is present on the given pixel and produce a more reliable result. While in the case of deep learning methods, we have more complex approaches. If you look at the first two lines, we can see that we have ARSET and CNNs, and we can see that they both have in common neural networks. The first one being recurrent, meaning that we're mostly working with time series, and CNNs, which are convolutional neural networks, which have made the name for themselves for tackling visual tasks, where we're using convolutions to aggregate the neighboring pixels and the information that they capture. And we can also take a look on the right side. This is a deep learning approach. As you can see, there are a lot of layers stacked on top of each other. This is quite often the case with deep learning methods as they become more and more complex, and they have more and more features that we need to tune. This is quite connected to the numbers of samples that are required in order to produce good results. And this is not always necessary, as some have already introduced us to a self-supervised pre-training option, meaning that we actually have time series that are not labeled and use those to pre-train our model to optimize the weight of the model, which is actually hidden which are hidden in all of these layers. And based on this, we are actually able to use much less information, much less samples to acquire quite impressive results. As you can see here are two examples where you can see that the accuracy increases with deep learning methods. We can go even further. We can actually knowledge transfer between different domains. As we mentioned before, this solution particular is not limited to any particular region or even a given task. It could be used for land use, land type classification, or just the specific crop types or specific forest types, or different really problems that we have defined ourselves. We can actually also transfer this model between years, but this means that we have to adapt a few things, specifically that we tell the model or that it is able to include this information of what year it is working with, or that it will be able to extrapolate what we have given it to apply and train and then test on the specific years that we're working with. While this will affect the results, we can achieve quite interesting knowledge transfer just by using the weights that have already been pre-trained for our model. We can actually optimize our model for a specific season, meaning that we don't use a calendar season, calendar year, as we usually do when preparing such data, because crops often grow quite differently from what our calendar year is. And this can be also then adapted to a specific region in the world. And once we even divide this information even further, we can do season adaptation, as crops can change within a given year and are specific to each individual season. But quite often, we don't actually need to be that specific. We don't need to be go that complex into the methods that we're using. In this particular case, to distinguish between extensive and intensive grasslands, this was the task that was given to us. And we decided to first look a little bit deeper into the time series that were made available. And we specifically then decided to use NDVI time series and coherence, meaning the change that has been observed for a specific pixel. And we noticed that doing each moving event, there's a drastic change in the time series, as you have seen before on the previous slide. And we actually only designed an algorithm that detects those changes. This could have been done with deep learning, but it is not necessary. And specifically why we didn't use it in this case was because the number of available samples to us was actually very small, and it would be too small to train a deep learning method, as it has too many parameters to optimize. But we have to keep in mind that we have to really be careful and inspect the data we're working with, because this is not always so simple. Mowing detection was one of the more nice examples of where this can be done, but we still needed to verify our results. In particular, we decided and we used the Haber generalization, which actually means that we looked at each individual region that we have in the country, and that has specific phonological changes that are actually specific to that region. And we can even see that that coincides with the distribution of extensive and intensive grasslands. And this is not specific just to 1 year. We can see here, we use 2 different years, and we can see that the pattern is persistent. There are some small changes, but we can see that in HAP1, meaning more of a Mediterranean region where the mowing is more frequent, we can see that the grasslands there are more intensively used, and this decreases, and it's almost the same in the HAP5, which is more of a alpine region, meaning that the grasslands there are mowed less often. And this is quite useful, as we can see, and that the intuition and the results that we have have been confirmed with an external source without just using the metrics that are available to us when we are using machine learning. And this can be quite often a good safety check to see that we are actually going or moving in the right direction. And now let us start with the practical workshop. You have already been given the access to the GitHub repository. It will be also shared in the chat. You can access it through this link and through this QR code. And we can take a look here. You can see that we're greeted with a repository. Here is a quick description on how you are able to access these files. You can use the git pull command or download the zip file. Once the file is downloaded, open the download directory, right-click on it, and extract it in the same folder. By double-clicking on it, we can see that we're greeted with the same file structure as in the repository. In particular, we'll be working with the data and notebooks folders. Similarly, we can move to this folder here in the repository, where we also have the particular instructions. By following the instructions here in the repository, we can see that we'll be using the Anaconda. You can download it from the official website. In particular, we'll be using the Anaconda prompt. Following the instructions, we can see that we first have to change our location. For me, this would be to change to download, ARSET -master, practical. You can see that first I added CD before the path. This means change directory. And now that we are in this folder, we can see that we are greeted with data, environment, and notebooks. In particular, we'll first need to create the environment. This can be done simply by copying the conda environment create command. And it will be using the environment.yaml file, which has all the required libraries defined. And simply by running the command, the environment will be prepared. If you will have any troubles with this, feel free to send me an email, but it should be running without a hitch. I have already done this command, so we will not be, there is no need to wait for it to finish. And now we need to activate the environment. This can be done using the conda activate command. And the name of our environment is the EO. And we can see that at the beginning, the name of the environment we're working with has changed. Now, as we are running in Python notebooks, we are going to need Jupyter Lab. Once you run this command, a new window will open, and you'll be greeted with the Jupyter environment. Similarly as before, we can see that we are in the same folder. We can open the notebooks, and this is where we'll be starting. Once we were able to establish our environment and run the Jupyter Lab, we can first get our credentials, which will be used by our Jupyter notebook and our program to download and access the data that we'll be taking a look at. In particular, we'll be needing three parameters. One will be instance ID, client ID, and client secret. This can all be found in Sentinel Hub dashboard. You have already created this account, and if you have not sent me an email, please do so now, and we'll be also crediting you additional credits, so you'll be able to access and process more data. But in particular, what we need to do first is actually go under dashboard. We can see there's the configuration utility, and you have to click this green button, which will enable you to create a new configuration. You can name it however you desire, but you should make sure to select the Python script template and then create the configuration. With this, you will have your first variable that we'll need to define. This will be instance ID, and it can be found and copied under this ID column. To find the other two, you will have to go under authorized clients, which can be found in the user set. In particular, you will first need to create a new authorized client. You can also name it based on the workshop or something similar of meaning, but you will have to make sure that you will save the secret key, as it will be shown only once, and it will be used to access the portal on all the data, and to make sure not to share it with anyone, as this is actually tied to the quota that you can use for how much imagery you can download and process with the given platform. I will not be showing these steps in detail as they are represented here, as we would need to blur out my personal information. Similarly, as anyone could use it to access our platform. So if we take a look at how the practical actually is divided, now that we have already signed up, we are able to use the credentials _ Sentinel Hub IPython notebook. We first have to also configure the Sentinel Hub.id file, which will be storing our credentials, and we'll then just be confirming the configuration that we'll be using. Then going on, we'll be using the Data Source Explorer, where we'll take a look at the data collection that is made available to us through the Sentinel Hub. We'll take a look at the eval script and see what changes can be made and how this affects our processing, together with an example of imagery retrieval and an example of a simple visualization. Going forward, we'll be taking a look at the Earth observation with state API. In particular, we'll take a look at a specific AOE read and how we can download the specific time series for the provided geometries. while also visualizing the time series that have been acquired. Then afterwards, there is an extra notebook that will not be able to take a look entirely, but we will briefly review it. We will take a look at the extra land cover notebook, but we will not go too much into detail, as it actually encompasses all of the previous notebooks, and it is actually the entire procedure. One would need to split a big area of interest, download the necessary data, add the reference, and do the required machine learning to achieve and produce classification map. And now if we start first with the first notebook, the credentials, we can go back to the browser and open the credentials sh.ipython notebook. This can be done simply by double-clicking on it, and we'll are greeted with a new tab. And in here we can see that we have the Sentinel Hub ID file, which can also be found here on the left side. And if we double-click it, we can see that here is actually where we'll be inputting our information: the instance ID, client ID, and client secret. I will be closing this window, and I will not be running this command, as this would actually reveal my credentials, and I'll be simply copying and moving my already predefined credentials into the notebooks folder and overwriting my existing file. Simply for you, we'll be just running this command and then following the following cell, as this will actually be the one that will configure your environment, and you will have 3 lines outputted below, which will be each individual value being set up. And then just to confirm that everything is valid, you also run the left cell, and you will have the output where the values will have been set. And now with the first notebook done, we can move forward to the data source explorer. And here we can take a look at the data collection, the eval script, and the image retrieval procedure, and the visualizations of the data itself. To prepare a little bit in advance, I have made I have already divided the area of Denmark into smaller regions. In particular, we'll be working with one EO patch that I have selected, and we'll be downloading the data and visualizing it in the Jupyter notebook. Going back to the notebook, we can open the data source explorer IPython notebook. We can see the data source exploration starts with the libraries import cell, which defines the functions that we'll be using in this notebook to load and process the data that we're working with. In the second cell, we'll be also defining the data folder in which we can find our Denmark_bbox GeoJSON file. This will be used to load the area we'll be working with. Here in the first section of the notebook, we already are presented with the Sentinel-2 L1C collection. In particular, we'll be downloading the RGB channels, the band 4, 3, and 2. As I'm sure you're all quite familiar with the NDVR, here is also an example on how to download these particular values without downloading the entire image. We can actually calculate this already in the cloud. We have to define the eval script, which has the channels already defined. In particular, we'll be working with band 4 and band 8. We'll also have to name the layer that we'll be working with. And here at the bottom, we have the function in which we pass the 2 before mentioned channels and the operation in which we'll be calculating them. Similarly to before, we have to define the Sentinel Hub task. In this case, we only need to pass the script that we'll be using to calculate it, and the layer on which you want to calculate the value on. As you might have noticed, both of them also, both of the tasks have one parameter that I have not mentioned. This is max cloud coverage, which means how many clouds can be on the image in order for it to be still included in the process. The higher this value is, the more clouds we permit to be included in the process. In our particular case, we'll be taking a look at the images in the year 2019. As well, this is the patch that I have selected in order for us to further explore the EOLearn notebooks. And now we are actually going to download the data. And this is done by executing the tasks that we have defined before. The only things that we are still missing are the bounding box and the time interval that we have defined in the cell above. This can be simply done by running this cell as well. And in the background, we are reaching Sentinel Hub services to download the data. And by already defining this interval and area, Sentinel Hub is already cropping the available images. And once the patches are downloaded, you can already see here that we have 19 images with 1000 by 1000 pixels approximately with 3 bands. This is what we have already defined in the beginning, and which is the RGB colors. Similarly, this needs to be run for the NDVI test, which will be completely a bit faster as we are transferring less data and doing the calculation in the cloud, which is also faster and more powerful than each individual machine. Similarly, we can also see what timestamps are available to us, and this should be the same and should not differ between the two different acquisitions that we have done. One of the tasks have completed. We can see the similar output as before, but now we actually have just one channel, and it's added under data and NDVI. And similarly as before, you can see that we still have the RGB values, and this is all joined in a single EO patch that can then be used and referenced individually. The timestamps are exactly the same as before, but now we can see when exactly the images have been acquired. Once the data has been downloaded, we can simply reference what subsection we want to be working with, in particular the RGB values in this case, and visualize them simply by using the AXImShow function, which will be taking the individual type step that we want to take a look at and displaying the image that we want to see. Similarly, we can calculate the median values, which can also show us how the observed area would look like without clouds, as we can expect those values to be much higher. Similar procedure can be done with NDVI. When we are presented with the values and the vegetation, and we can see quite well where the areas of urban and vegetation differ. We can quite simply also calculate the NDVI time series by specifying an area that we want to calculate it for, and then plotting the values. A similar procedure can be applied to Sentinel-1 data. We only need to change the data collection that we are using. Here it is changed to Sentinel-1 descending, and also the bands and band features that we want to be working with. Here we are specifying the descending and the ascending track. If you are interested in any more detailed information about the data that is available, it can be found on the Sentinel Hub repository under the docs.sentinel-hub.com. And you can here read about each individual data source, that is how it is being processed, acquisitioned, and in what shape or form it is available in the Sentinel Hub. Similarly as before, we can run the task of just downloading the data for the desired area and interval. Once the data is downloaded, we can visualize it similarly as before, but in this case, we can take a look at the percentile calculations, the 80th and the 20th percentile, while also visualizing the standard deviation under the blue band. Simply, we can do this by predefining the variables for each channel and then constructing and concatenating the array and then visualizing it as an image. There are various ways of joining this information and how we can combine it, depending on what we want to emphasize in each individual image. And in this way, we can actually also see and compare different images or acquisition times. If we take a look at a particular example, we can take a look at having the first image as red, the third image as green, and the 11th as blue. And we can see how the area changed throughout the year and how the acquired images represent that. We can see that, as we mentioned, that we have the blue values being the latest change, meaning that wherever there is blue, the values were the highest only for the last image. And now, before we start with the third notebook, the Sentinel Hub actually has data in various, we can access the Sentinel Hub data in various shapes or forms. In particular, we'll be taking a look at VCS request using a script that is actually written in Python similarly as before, but the main difference is using the Sentinel Hub statistical API. And we can do this by using a GeoJSON. And why is this important is actually because we can specify, as you can see here, an example of a GeoJSON format, the areas where we want the data to acquire the data. In particular, we have here marked 5 different fields, regions, an example of a meadow, of agriculture, water, forest, and urban. Similarly, you can see them here. And we'll be taking a look at how actually we can access this data almost instantly without even downloading the images, only downloading the specific time series. Starting with the third notebook, the retrieval of data using a statistical API. Similarly as before, we have the importing of libraries in the first few cells. And specifically, we'll be adding the Sentinel Hub statistical download client and Sentinel Hub statistical. And we have a few helper functions in the beginning, which will enable us to parse the information that we'll be acquiring. Similarly to before as well, we have the eval script, but in this case, we'll be accessing all the bands. And you can see now that we're also adding a CLME and CLP layers, which are in particular masks and are used to mask the data as cloud mask and cloud probability. As before, we can also add the NDVI values. We can see here that we have each pixel being evaluated and by predefined equations. You can also add your own just simply by following these procedures. We'll be taking a look at Kran. This is a town in Slovenia. And similarly as we have done before, we can specify a bounding box and the time interval that we want to work with. Before we download the statistics for the region, we can first take a look at what information, what area we are working with. As before, we can specify the collection, but in this case, the difference being we'll be using a VCS request, but we will be again defining the layer, which is the true color, and downloading it at 60-meter resolution. Additionally, here you can see that we have specified a data folder. This means that whenever we'll be re-requesting these images, the script will first check if we have already downloaded them. So this procedure will not be rerunning and re-downloading and using our quota necessarily. In this case, you can see we have acquired 37 images, and we can start by visualizing a few of them. We can see that in this particular case, the area on the first image was not cloudy, while this is not the case for all of the images, but this can be later handled and processed in the later steps. But what we are in particularly and most interested in is calculating the information already in the cloud and then just downloading the time series. This can be done with the Sentinel Hub statistic package. And here we additionally specify the interval that we want to operate with. This defines when, at what time steps we'll be aggregating the information that we have. We have to define the calculations that we'll be using. This means what values will be aggregated and returned to us. In some cases, we want to calculate the mean or median, but this can just be specified and passed in the calculations and then adjusted based on the individual area when and what we are working with. Similarly as before, we now are actually able to join all of these predefined attributes into the Sentinel Hub statistical function, which will be actually getting us the data. When you'll be running this function for the first time, you can expect it to take quite longer. As this data is already accessible on my PC, it only needed to read it from the cache folder and load it into RAM. In case you have any errors, they look like this, and you can just make sure that the request that you're sending is not being timed out, or that you don't have any issues with the processing before proceeding forward. And this can be simply the values that we have received can be simply viewed by specifying the data and then the actual inputs, the output of each individual time step. But now, before we visualize the time series, we would like to reformat the data so it can be easier or simpler to understand. This can be done by just changing it into a data frame and changing all of the values into columns. We can still see here that we have values for each individual band and the percentiles as we have them defined before. As you might have noticed, the values range around 5,000. This is done so that we do not transfer float values over as they require much more data and take longer to transfer. Now that we have already prepared our table, we can go forward and visualize the information that we have acquired. We can see the values now are distributed, at least for ND1, between -1 and 1. And we can also confirm this on the graph. But now we can see that the values and the time series is really jacked. We would need to further remove the clouds in order to improve this visualization. What we have done above was actually for the whole area of crown. but what we're interested in particular is actually just the geometries and the particular types of land that we have specified in our GeoJSON file. We have to first make sure that it is in the right projection, and then we can simply pass on the request to Sentinel Hub statistical client, and it will download the data for us. Once the download has finished, we can check and we can see that we have exactly as many time series as we have specified in our data frame. Again, similarly as before, we have to normalize the data. The values are around 5,000. And now we can simply visualize our time series. And we can see the time series are quite jagged as well, but this is due to clouds, which can be removed. Simply, we can mask them using the CLME value, and we can see the values have already improved. But we also have one additional option to filter by CLP, but this I will let for you to try out and test in your own notebooks. Before going to the final notebook, we will take a look at the standard procedure in EOLERN by defining the region of interest similarly as we have done before. In this case, for extracting the water extent, we can see that we simply download the satellite imagery for a specific region, mask the clouds, extract and calculate the NDVI feature, use the threshold, and then we can simply vectorize the extent and save the result. As you can see, the procedure is quite straightforward, and so this is can be made, and it's simple because of EO workflows that we can apply on any region, any area of interest that we have at our disposal or that we have reference data for, and simply by defining the area that we're interested, the country, we can split it into smaller tiles, download the information for each individual one, and then use any complex method or processing in order to achieve the required result. The last notebook in particular shows how we can do machine learning for our example. And as we have some time constraints, we'll be only overviewing the notebook, but you're more than welcome to run it yourself, as you will have more than enough credits to process this data and acquire it. In case you will have any different applications or desires, here on the right side are also a few more examples that are available on the EOLERN workflows and workshops, and you will be able to find something that suits your needs. And if you have any particular requests or questions, you are more than welcome to write and address them to me. And now to the last notebook. The last notebook is a guide on how to create land use, land cover predictions. In this particular case for Slovenia, it's divided into parts. We'll not be running through them, but a quick overview would be that in the first part, we are actually preparing the data, preparing the dividing the region, and only taking a look at the 5x5 area, as this is quite a hefty task. And a 5x5 area is manageable for most computers, and it's a great start. But you can also change this later to any country or to any area size or any year of your particular desire. In the second step, the data is downloaded using Sentinel Hub PI package, and then the NDVI index and water index is calculated, while we also add the reference map, which is also provided in the repository. In the second part, the data preparation for machine learning takes part, including the construction of the model and training, and then also validating the model and visualizing the results. Similarly as before, we are first greeted by the imports, and then, as mentioned, the area definition and visualizing it, while in the second to the fourth, we'll be actually downloading the data, defining the tasks that will be adding it, and defining the workflows in order for us to automate the procedure. Here are a few definitions of the land use land cover map and the colors that will be used in the end to visualize everything. Here is also the reference that is being used. It consists of the 10 classes mentioned before, and here is the entire procedure summarized again. In case you will have any questions, you will also be able to email us, but the script should be working without any issues, and it also has some good visualizations which will be showing you if you are on the right path and how the data that you're working with is actually looks like, and how it changes throughout the year. And in the second part, as mentioned, is the machine learning data preparation and procedure. Well, you'll be actually running the model and training and running the model on the patches that have been previously downloaded. Here is the entire model training. First, we simply have to prepare the data in order for the model to train on it. We here divide it into train and test set, which is then used as the input onto the LGBM classifier. And you can save it on your computer, so you can use it at any other time and see how the results compare between different runs in case you'll be changing the parameters or any particular input to the model. Here you can also visualize the confusion matrix, which will actually indicate and tell you how well the model performs. But more, I suggest that a more in-depth information that you find it on the internet, as there is a lot of interesting things that can be optimized depending on what is the problem that you're dealing with, including different metrics that can visualize your model performance. You can also evaluate which features are among the most important for the given task that you're working with, and you can also visualize how and what information was done by the model, what was predicted by it, and save it as a TIFF in order to be viewed in any other spatial program that you prefer. With this, I would conclude the practical part and would like to invite you to change and switch up the parameters that you have been using and the area of interest that you want to be working with. In particular, I would encourage you to use the statistical API, as you can calculate and get a lot of information for any particular region that you're working with or points of interest without much complication and quite quickly, as you do not need to download the images and the entire images to your local computer. With this, I welcome you to also to write us an email in case you have any questions, and would like to thank the organizers and Krištof for providing us with this informative workshop.
Krištof and Matej, thank you for the wonderful presentation and demonstration. We will now transition to the question and answer portion of today's training. Please enter your questions in the question and answer box, and we will get to them in the order they were received. We will post the question and answer document to the training webpage before the start of next week's training. Below is the contact information for Krištof and Matej, along with links to the training webpage, website, and social media. If you enjoyed today's webinar, we hope you will sign up on the ARSET listserv to receive notifications of future trainings. And please follow us on Twitter for future relevant announcements pertaining to NASA's Earth Sciences.
We've been receiving a lot of terrific questions so far. I want to thank everybody that has submitted a question. We still have about 25 minutes left in the session, so there is still time. If you have a question that you want to ask either Dr. Oštir or Matej, please do put it in the question box, and we'll get to it as soon as we can. So question number 1, could you please tell us more about the harmonized Landsat Sentinel or HLS availability on Sentinel Hub? How do we access it?
So the harmonized Landsat Sentinel data is available on Sentinel Hub in the same way as any other data. So the Sentinel-1, Sentinel-2, Sentinel-3, and Landsat 8, 7, and so on. We have listed here a description of the data set, and it's easy to get it either through EO browser or through statistical API. So what Matej has shown can be done also with harmonized Landsat Sentinel dataset.
Wonderful. Question number 2, how do we classify crop types in tropical areas, especially in proximity to forests? I imagine that the NDVI fluctuations might be smaller, so we are more likely to misclassify crops.
Maybe I'll answer this one, if you can hear me, of course.
Matej, we can hear you just fine. Thank you.
Wonderful. Okay, so actually the NDVI changes depending on what vegetation can be found in a particular area. And actually it would be misclassified only if the signal would be really similar. That is why it's really important that we have a strong signal for each class that we're actually trying to classify, and it really is dependent on the training samples that we are using. So actually once we have this, we can explore how and what classes are actually phenologically similar when we are working with the data.
If I may just add, maybe NDVI or optical data would not be enough for tropical areas. So you have to use also the radar data.
Wonderful. Question number 3. Since the central wavelengths on Sentinel-2A and B differ slightly, is that something we should take into account or somehow correct for when using images from both satellites, example given for classification purposes?
No, the answer here is no. These are almost identical satellites. The slide that I have shown is just a demonstration that they are not exactly the same satellites because they have been built in different phases with different methodology, but the user does not have to make any differentiation between S2A and B.
Great. Well, hopefully that puts a concerned mind to rest, that you can use both of those interchangeably. Question number 4.
But there might be something, but the geometry of Sentinel-2 and Sentinel-2A and B is not exactly the same. So it's the pixel shifts can be bigger between the two satellites than the spectral reflectance changes.
Okay, question 4. Do you normalize the crop time signatures by latitude or for seasonal weather? The growth curve for any crop will vary by the date planted, the weather, and the growing degree days.
Yes, this is true, and it would play a big role if we would be producing a map for a continent, but we would have to adapt the calculation and the areas and calculate everything connected to that. But this is not especially adapted to multiple seasons or within a year that we're working with. That is why we usually use deep learning. and we let it learn the features, and it can do it so by inferring it during training. And this is actually a specific topic that can be also explored. And if you're really interested into it, I suggest that you look at knowledge transfer and concept shift, just to name a few.
Wonderful. And question, thank you, Matej. Question number 5. Is Sentinel Hub free to access? Is it possible for a student not to pay for that subscription?
Yeah, the short answer is Sentinel Hub is not for free for commercial purposes. However, the basic functionality of Sentinel Hub is free. It's both Sentinel Hub and EU browser, and there exists a lot of sponsorship, especially for researchers, scientists, and students. I would like to invite you to have a look at the ESA Network of Resources web page, where you can apply for sponsorship for Sentinel Hub, but also other services that ESA is sponsoring. And all the ARSET participants, if they register and email their registered email to Matej, will get sponsorship through the same network.
Terrific. That is wonderful. And thank you both Matej and Krištof for helping to organize those sponsorships for these participants. Very much appreciated. Question number 6. Is the data from Sentinel Hub original data or somewhat downscaled?
No, this is a very important question, and it comes several times regarding the data. No, it's the same data that is being used if you download the data from any platform. So the original files are the same. However, if you are looking at the EU browser, of course, the image that you see is reduced because there's no need to have the original raw data. If you are just looking at a large area, so a city or even a region, and it is therefore computed on the fly from the original data, resampled and computed. So, but you can get through Sentinel Hub, especially through statistical API, the original data in a matrix form. So you can get an array or X-array or NumPy array with the original values. And in addition to that, you can get subsampled values. So different spatial and spectral subsampling. It's the same way as you subsample metrics in Python. Very similar way you could get subsample data from the Sentinel Hub.
Great, thank you,
And
Krištof.
if I add the statistical API and actually just downloading the data from Sentinel Hub, you quite often can accompany Sentinel-2 at least with CLP, which is the cloud probability mask, which is a bit of an improvement from what is originally available. So you're able to mask the clouds a little bit better.
Yeah, that's thanks, Matej, for pointing this out. The data is actually supplemented by additional masks and additional information that is very useful for statistical analysis.
Great, thank you both, Krištof and Matej. Question 7, are the points in the time series representative of each period, example like a month, or is it the chosen area's mean?
Okay, the samples that we have been showing are an average of our spatial average. So we have selected a length parcel, and you can select many parcels. You can have vector data for this, and the average or basic statistics for that area, mean, minimum, maximum, standard deviation, are computed for each timestamp. So you get the statistics for each timestamp. However, the statistical API also enables you to do the time aggregation of the data, like computing the maximum value in a certain period of time, or computing the average value in a month, in a week. That is being performed in the cloud, and when you are getting back the statistics, this is the information that you are getting. So the answer is, for a particular point in time, you get the spatial statistics for the area.
Thank you, Krištof. Question 8. Does Sentinel Hub support exporting .csv stats via the API or only through the browser as shown?
Matej, if you want, you can answer. Basically, yes. we have started with EO browser just for demonstration purposes, but Matej, you can go on.
Yeah, but we would quite often actually suggest using the Python script that we have added, and you actually have way more options, and you're very flexible in what formats, what are you doing, what are you using. So really you can explore many different various things and analysis once using the Python API.
I would say if for basic playing, you could just use EO browser, select the area and download the CSV and explore it in Excel. But for any practical work, statistical API is the way to go.
Great. Question 9 is very similar to question 2 that we received earlier. Has to do with the vegetation index in the tropics. So how important is the NDVI method for monitoring crops in the tropical areas because of the cloud cover?
Yes, this is similar to the question before. The solution to monitor crops in the tropics is to use radar in combination with optical data, because the cloud coverage is for any area where the cloud coverage is high, radar might be the only option. But when we are using machine learning, especially deep learning, we can use radar. We can use radar to compute the NDVI data from it, and we have included here a link to a paper where radar Sentinel-1 was used to compute the NDVI and then use these simulated or computed values for time series analysis.
Great. Question number 10. In the Sentinel Hub EO browser, can we upload ground truth shapefiles of area of interest for getting time series? And can we download the results of analysis, or do we require a license?
Yes, you can download the statistics on any shape that you have provided, and you will be actually able to download it similarly to what we did now during the examples that we've shown, but you would not require a license to do so, and you're free to share these data as well.
Wonderful. Question number 11. Is maintaining the balance of the classes or the number of class-specific pixels in the mask essential when classifying something or making a mask necessary? For instance, 90 pixels for a woodland, 100 pixels for water, etc.
Yeah, and this is quite important, especially depending on what machine learning model you're using. But quite often, when you have such minor differences, this is not a problem. But when it's, for example, a 90% difference between the majority and the other classes, this needs to be addressed. And we have to adapt our model, our training, our machine learning to this. But this is also quite connected to what we're trying to achieve with the machine learning that we're doing. So usually you iterate, you choose something, one of these approaches, and then you see what actually is able to bring you closer to the desired result.
Great, thank you, Matej. Question number 12. It asks, how small was your sample?
Our sample in the EO browser was, of course, quite small. It was half a square kilometer, but this was just for demonstration purposes. You could see that we have computed the statistics in real time, and however, you can use larger area, multiple polygons, and compute the statistics on a rather large area, or let's say a smaller region or something like that. However, be aware and monitor the Sentinel Hub data processing usage in the Sentinel Hub dashboard.
Great. Question number 13. How do you classify those crops which have very similar phenology cycles? Example, barley and wheat, or sorghum and pearl millet?
This actually can pose quite a problem, and it's difficult, but it's really important, even more important in these cases, that we have a good training data set, because otherwise the accuracy will be low, and we will be confusing the classes. And we usually expect that the dominant crop, actually the one that occurs more often, will have a higher accuracy, but we might be able to overcome this with really dense time series or even multi-year data.
When we are talking about extremely dense time series, we are thinking about the planet data, which is actually daily data. Of course, the planet data is not available for free.
Wonderful. Question number 14. Can we work with all the 13 bands of Sentinel-2, and how seamless is it to use this to estimate biomass?
Well, if I start, yes, you can work with all the 13 bands coming from Sentinel-2. They are all available. As already mentioned, you can download the data and process the data. However, then you might use only 10-meter resolution data, so the 4 bands, the red, green, blue, and near-infrared data, or the 20-meter resolution data. They're both described on the Sentinel Hub, and it's almost the same. So have a look at the web page, and you will see that it is very seamlessly to use either level 1C or level 2A data with all the bands or a subset of bands. But have also in mind that you can use also the indices. So you can compute several vegetation and other indices, and forget about the raw bands and use just indices time series. And regarding the biomass estimation, there are studies on estimating biomass using Sentinel-2 data, but the results depend on of course, the quality of reference data, and you might require also LiDAR, radar data, and similar sensors.
18 is, how can we set a specific range of each band to display a satellite image? Example, band 4 in the red channel with a limit of 0 to 0.5% reflectance, likewise for other RGB bands.
Yes, this is a very good question, and the answer is yes, you can change the visualizations on EO browser. First, you can just select different bands, and then you can use custom scripts for the visualization. And custom scripts are actually JavaScripts where you can specify the range of the bands, you can compute the statistics, you can compute the minimum, the maximum, the percentage that is displayed. And these JavaScripts can also be more complex. They can compute different indices, as I already mentioned, or they can make other visualization like thresholding and so on. So it is a very, very efficient way. And this JavaScripting interface can be used both with EO browser for immediate visualization, but also as an input for Sentinel Hub's API. So you can use the same script to get the data visualized in EO browser, or compute the statistics computed with Sentinel Hub API. There's actually a web page with the custom scripts that are available, and you can get all the scripts or many scripts on GitHub already. The link to the page will be listed in the notes.
Great. Question number 19 has to deal with interferograms. So how do you generate interferograms from Sentinel-1 data?
Generating interferograms with the stream is still frozen on my side, so I don't know if this has been resolved. So to generate interferograms, we are using Snap. Snap is a software that is available for free from European Space Agency, and it is a very useful software for processing both optical and radar data. And if you want to generate interferograms with Sentinel-1 data, you have to download single-look complex data. And then you can process this data locally, either manually with Snap or automatically with Python scripts and Snap graphical workflow. And this takes quite some time. So there will be a link to Snap download and to tutorial for processing this data. And in addition to that, we have been speaking about the access to the Copernicus data through different platforms. And one of the platforms is called CreoDias, which is not free. And this is, according to my knowledge, the only one that has already pre-computed coherence data.
Okay, great. Thank you, Krištof. Question 20. Where can I find the information I need to fill the instance ID, client ID, and client secret fields in the sentinelhub.id file?
This information can be found in the Sentinel Hub dashboard. And if you'll go through the recording again in a self-paced, you'll be able to see there is a slide where it is specifically specified that instance ID can be found under configuration ID utility, client ID can be found under user settings, and while the secret ID client secret will be actually visible once you create a new client and you will decide on what to name it, and you will be able to see the secret, but only for one time. So make sure to copy it somewhere.
Great. Thank you, Matej. Well, we are nearing the top of, or I guess the end of the training. We have 2 minutes left. As we conclude the second part of the training, the English session, as we wrap up, I did want to give both Dr. Oštir and Matej Račič an opportunity to maybe any closing thoughts or comments that they might have for the participants that are still on today's call. And Dr. Oštir, why don't we start with you?
Okay, thanks. It was a pleasure talking to the participants, answer their questions. Yes, I believe that we live in a wonderful time for observation. We have dense or very dense time series. We have all or almost all the data that we need. Now we have to use this data wisely, and we have to use machine learning methods, but not methods. But we have to be careful to provide very good or clever solutions to our environment. There was also a question regarding Sentinel Hub, as in the frame that Planet has bought Sentinel Hub. I believe that not a lot will change with Sentinel Hub. The company will remain, even in the frame of Planet, it will remain providing the same services. It will be actually even better integrated with other data.
And Matej, did you have any closing thoughts or comments for the participants?
Yeah, thank you. Yeah, it was quite a pleasure, and seeing so many questions, I really am looking forward to what advances will be there, and hoping to see all of you on any upcoming conferences to share and see what we have been up to.
And don't forget to use the Sentinel Hub credentials you have.
Yes, this is a terrific opportunity for everybody that's participating in this training. We do strongly encourage you, go explore Sentinel Hub, see its applications, its utility for your own research, for your own work. If it's, if it's some type of operational work that you're doing in the field of agriculture, et cetera, definitely do take advantage of this opportunity and the credentials that you have to explore Sentinel Hub. It's a really great opportunity that is being provided. We want to thank very, very much to Dr. Krištof Oštir and Matej Račič for an amazing presentation and demonstration. Thank you both so much. For all the participants, we will be, if we did not address your question, because unfortunately we're out of time, but we will finish answering all of your questions, and we will post this doc to the training page by next week. So next Tuesday, when we have the final part of this webinar series, we hope to have this finished, edited, and on there so that you can get an answer to your question if it was not answered today. So thank you to all the participants. We wherever you're joining from, whatever time zone you're in, we greatly appreciate you joining us today. And lastly, I want to thank the ARSET team who's working in the background to make this training possible. That's Sarah Cutshall, Brock Blevins, and Natasha. So thank you everybody for joining, and we look forward to seeing you in our last part of the webinar series next Tuesday. Goodbye.